Back in school, we were taught that earthquakes happen when two tectonic plates brush past each other. But what are tectonic plates? What makes them move in the first place? Why is the African continent tearing itself apart and a piece of it is heading straight for India? Why is the longest mountain range on Earth underwater? And what on earth are supercontinents? All of these questions lead us to one fascinating scientific theory, the theory of plate tectonics. In this video, I'm going to break down this theory of plate tectonics into simple, easy to grasp concepts. No jargon, no confusion, just straight up clarity, so that by the end of this video, you will be able to answer every single one of those questions by yourself. Let's dive in. Before we get to the theory of plate tectonics, I'll give you a basic idea of the internal structure of Earth. We know Earth is made of three layers: the crust, the mantle, and the core. The layer from the surface of the Earth to a depth of 50 kilometers is the crust. Mantle is from the bottom of the crust to a depth of 3000 kilometers. And finally, the core is from the bottom of the mantle to a depth of 6400 kilometers, which is the radius of the Earth. But this is a classification based on the chemical composition of the rocks that make up these layers. For instance, silicon is the key element of crustal rocks. Mantle, on the other hand, contains not just silicon but also iron and magnesium. Core is predominantly made of iron. Let us set aside this chemical classification for a moment, because plate tectonics has got more to do with physics than chemistry. So to understand it better, we need a more physical classification. A classification based on the state of matter of these layers, whether the layers are solid or liquid or semi-solid, that sort of thing. So let's take a trip down to the center of the Earth. We will begin from where we are standing. This layer touching your feet, assuming you're standing on the ground, is called the lithosphere. It extends to a depth of 100 kilometers and is solid. So, the lithosphere is the entire crust plus the upper mantle or the solid layer of mantle. At the bottom of the lithosphere, the temperature is already 1300 degrees Celsius. The lithosphere is followed by asthenosphere, a 200 kilometer thick and semi-solid layer. The high temperature at these depths melts the rocks and makes them flow, but very slowly, like a highly viscous lava. At the bottom of the asthenosphere, the temperature is about 1500 degrees Celsius. Here, it is important to realize that all our continents and oceans, our high-rise buildings, all our bridges and roads, and all of the life are on the lithosphere, the solid layer, and this solid layer floats on a semi-solid layer called the asthenosphere. The asthenosphere is followed by the mesosphere, 3000 kilometer thick and solid layer. You might wonder, why solid again? Just remember that state of any matter not just depends on temperature but also pressure. The temperature at the bottom of this layer is as high as 3500 degrees Celsius. But the pressure from the 300 kilometer thick rocky layer above it keeps the rocks of this layer solid. The mesosphere is followed by the outer core, which is an ocean of liquid rock and extends to a depth of 5000 kilometers. And now for the last part, from 5000 kilometers until the center of the Earth, that is until 6400 kilometers, is called the inner core, a solid and hot iron ball measuring a temperature of 5500 degrees Celsius, which is equal to the temperature at the sun's surface. In summary, besides the three chemical layers, Earth also has 5 physical layers. From the top, a solid lithosphere floating on a semi-solid asthenosphere, followed by a solid mesosphere, then a liquid outer core, and finally the iron solid inner core. Now there are four key takeaways from this. First, the physical lithosphere layer contains entire crust plus upper mantle, which are chemical layers. Second, all of our continents and oceans are embedded into this lithosphere. Third, the solid lithosphere floats on the semi-solid asthenosphere. Fourth, and the most obvious one, the inside of Earth is extremely hot. Now that you have a good understanding of the internal structure of Earth, you are ready to know what exactly a tectonic plate is. Lithosphere, as I mentioned, is the solid and the outermost layer of Earth's surface floating on the semi-solid asthenosphere beneath it. Now, lithosphere is not one single landmass. Rather, it is broken up into multiple fragments called tectonic plates. The entire surface of Earth, or lithosphere, is a giant jigsaw puzzle, and each interlocking piece is a tectonic plate. That answers your first question of what a tectonic plate is. Earth's lithosphere is made up of about 20 tectonic plates today. Now, why is it all broken up? Let's go back to the moment when Earth had just formed. It looked something like this: a hot molten rock ball revolving around the sun. Eventually, by radiating heat, the surface of the Earth began to cool. Some areas of the Earth's surface cooled faster than their surroundings, solidified, and acted as a vent for Earth's heat. These solid land masses, through cooling, grew in size and covered the entire planet and became the OG tectonic plates. Of the 20 tectonic plates that exist today, 7 to 8 of these are huge ones, like the Antarctic plate, Eurasian plate, Indian plate, African plate, etc. It is important not to confuse continents with tectonic plates. A tectonic plate can only have a continent on it and no ocean at all, like the Eurasian plate. A tectonic plate can have both continent and an ocean on it, like the North American plate. A tectonic plate can be covered entirely with an ocean with no continent on it at all, like the Pacific plate. Now that we know what a tectonic plate is, let us understand what makes these plates move. Remember that the temperature of the insides of Earth is very high. This heat has two sources. Number one, the heat trapped inside the Earth from the time of formation of solar system. And number two, more important, is the heat from the decay of radioactive elements like uranium and thorium present inside the layers of Earth. This heat keeps the second layer, the asthenosphere, in a semi-solid state. And more importantly, it is the root cause for an interesting phenomenon that makes the plates move, called the mantle convection. What happens when you continuously heat a bowl of water? The water just above the source of heat heats up first. When the temperature rises, its density reduces and it moves upwards. In its upward path, it gives away the heat to surrounding water, and by the time it reaches top, it cools down and its density is increased again. But because the water behind it is pushing it and there is nowhere left to go, it moves to the side, hits the side of the bowl, and sinks to the bottom from the sides. A continuous churning of fluid, or convection. Now upscale this phenomenon to the insides of Earth. We have a heat source inside the Earth and a fluid, that is the asthenosphere, that is getting heated by this heat source from below. This causes a similar continuous churning of semi-solid rock inside the asthenosphere. When hot rock moving upwards due to internal heat reaches and hits the solid lithosphere, that is a tectonic plate, from the bottom, the molten rock moves sideways, dragging the plate above it along with it, causing it to move. This is called mantle convection and is the primary driver for plate tectonics. Now, this answers your second question of what makes the plates move. Answer: mantle convection. As far as the African continent is concerned, it now lies on two tectonic plates, the Nubian plate on the west and Somalian plate on the east. As of today, the mantle convection is making the Nubian plate move upwards at 2 centimeters per year speed into the Eurasian plate, while the Somalian plate is moving east-southeast at 2.5 centimeters per year, thus splitting up the continent. This answers the third question of why is the Africa splitting up. As I mentioned before, lithosphere is a giant jigsaw puzzle and each interlocking piece is a tectonic plate. Now when mantle convection drags the plate from below, because there are no gaps between the plates, these tectonic plates push into each other. The consequence of these plates pushing into each other literally shapes the earth. It determines how the surface of the earth looks like. Now that you have come so far into this theory, I want you to understand what are the various outcomes that are possible. With what you already know so far, this is going to be pretty intuitive. So stay with me. Each tectonic plate is a piece of lithosphere, a piece of upper mantle plus crust. All our continents and oceans are embedded into this lithosphere. For instance, the North Atlantic plate has a continent, or in other words, covered by continental crust on the west, and has Atlantic Ocean, or covered by oceanic crust on the east. Although the mantle layer under the continent portion is same as the mantle under the oceanic portion, the crust making up the continent is different from the crust under the ocean, both in composition and, more important in this context, in density. The ocean crust is denser than the continental crust, and as a result, they float at different heights in the asthenosphere. I want you to keep this at the back of your head. We'll need it in a moment. Now, two plates can move into each other, resulting in a converging boundary. Two plates can move away from each other, resulting in a diverging boundary, or two plates can move past each other, resulting in a transform boundary. Three things can happen at a convergent boundary. If at the convergent boundary, both plates have continental crust, both plates fold upwards at the boundary and mountains are created, like our Himalayas. If at the convergent boundary, both plates have oceanic crust, the plates with lesser density goes under the higher density plate. The upward moving plate creates island arcs like Japan, while the downward moving plate descends into the asthenosphere, melts and becomes one with it. This is called subduction. If at the convergent boundary, one of them has continental crust and the other is of oceanic crust, remember what we discussed earlier, because of its higher density, the oceanic crust subducts under the continental crust plate. Similarly, three things can happen at a divergent boundary as well. If at the divergent boundary, both plates have continental crust, the plate becomes thin and the crust readjusts and descends, creating a rift valley. And ultimately, in a few million years, water pours in from the sides and an ocean is created in the rift. If at the divergent boundary, both plates have oceanic crust, the semi-solid asthenospheric rock pours into this gap from below, creating a new lithosphere under the ocean. This rock that pours out piles up, forming an underwater ridge, like the Mid-Atlantic Ocean Ridge. This is called seafloor spreading. If at the divergent boundary, one of them has continental crust and the other is of oceanic crust, the consequence is similar to both plates having oceanic crust. The 65,000 kilometer long mid-ocean ridge system is the best example for the divergent boundary between two plates with oceanic crusts on either side of the boundary. It is the longest continuous mountain range. For perspective, the next longest mountain range on Earth is Andes, which is 7,000 kilometers, 9 times shorter than this underwater mountain range. This answers the fourth question of why is the longest mountain range on Earth underwater. It is important that we realize that if a plate is getting subducted and destroyed at a convergent boundary here, then another plate must be getting created at a divergent boundary at some other place. This is called plate recycling and is happening as we speak. This is why the OG tectonic plates are different from the tectonic plates that we have today. A supercontinent is one giant landmass or most landmass of Earth's surface concentrated in one single place and surrounded by a vast ocean. This might sound like science fiction, but there were instances, in fact, 7 instances in the 4.5 billion years of Earth's history, when all the landmass is concentrated in one single place. Over time, the supercontinent would break apart, but after a few million years, come together again and form another supercontinent. Pangaea was the most recent supercontinent and looked something like this. Pangaea existed between 335 to 175 million years ago, which is to say that it formed 335 million years ago and broke up 175 million years ago. It was the most recent time in Earth's history when all the continents were joined together as one massive landmass and was surrounded by a vast universal ocean. When the breaking up began 175 million years ago, Pangaea broke into Laurasia in the north and Gondwana in the south. The Indian plate was a part of Gondwana, along with the most southern land masses like Australia, Antarctica, South America, and Africa. South American and African plates were the first to break away from Gondwana and from each other, causing the formation of Atlantic Ocean. About 125 million years ago, when dinosaurs were at their peak dominance on Earth, the Indian plate, along with modern day Madagascar, together broke up from the remaining landmass and moved towards the Eurasian plate. Soon after, about 90 million years ago, India separated from Madagascar and started its journey towards the Eurasian plate. At about 50 million years ago mark, down in the south, the Australian plate and the Antarctic plate both began to separate, while up here, the Indian plate hit the Eurasian plate, creating the Himalayas. But why do these supercontinents form and break apart, causing a supercontinent cycle of sorts? This has got to do with our dear old mantle convection and a sprinkle of luck. As I said, if at the converging boundary one of the plates have oceanic crust, then the oceanic crust will get subducted and destroyed. Sometimes it so happens that the subduction will continue until all the oceanic crust gets destroyed and the continental crust of both the plates meet. Now, if mantle convection works in such a way that it pushes all the plates together and simultaneously, then the oceanic crust in between the continental crust of these plates gets subducted and destroyed, thereby forming a group of plates with their continental crust concentrated in one single location, or a giant landmass called a supercontinent. This answers the fifth and the last question. In this video, we took a deep dive into the Earth's interior to look at its 5 physical layers, understood what tectonic plates are and what makes them move, how tectonic plates interact at their boundaries to create mountains, islands, and subduction zones, and what supercontinents are. Knowing this makes us realize how the Earth and its interiors are more dynamic than we assume, although the pace at which these changes happen is slow and spread over millions of years. If this has amazed you, it means I've done my job well. Thank you so much for watching. If you liked the video and learned something new, please consider giving it a like. Until next time, this is Sandeep. You are watching The Curious Octopus. Keep asking why. This video is the second of the 6 episodes of the video series called Workings of the World. First 5 episodes titled Origin Story of the Moon, all about plate tectonics, ice ages and seasons, extinction events, origin story of man. Each have an exciting story to tell. And the finale, the 6th episode, titled The Biography of Earth, will build on these 5 episodes to give you a big picture understanding of our blue planet and the amazing events and phenomena that have shaped and are still shaping it, from the moment it took birth 4.5 billion years ago until now. If this has gotten you excited, I think you should hit the subscribe button below. And that way, whenever a new episode is released, you will get notified. Thank you for watching.